Hello everybody, welcome back to chemistry first day. I'm glad that we are moving towards S2. Remember, S1 is a particular nature of matter, and S2 is about model of the bonding between molecules, between atoms, how they form molecules, how they form ionic compounds. Okay, it's a very funny, interesting part. Okay, the first one is ionic model, how ionic compounds are formed. So we are on structural tools, okay, models of bonding and structures. And the first one we encounter is S2.1, the Ionic model. Okay. So first of all, about ionic compound. First of all, we talk about how ions are formed. So charge of ions. Okay. This is a concept of the foundation is from the electronic configuration. For the fully occupied electron shell is the most stable. So the atom wants to be ion. That's fulfilling these rules. We call it octet rules. Okay. So as for metal ions, they will lose electron, tends to lose electron and forming a positive ion. Positive ion, you need to remember the name is cation. You remember it, I'm sure. For non-metal atoms, okay, to gain electrons, they will form negative ion, they will form anion. So by the periodic table, left hand side is the metal. They will lose the electron accordingly. Okay, the outermost shell electron in the S1, S2, and P1 will be loosed again and form the octet number according to fully filled shell. Okay, they become A plus, A2 plus, A3 plus, depends on how many electrons are extra than the octet rules. Okay, and for the opposite, for the non-metal, they want to get one more electron, two more electron, and three more electron to be fully filled. So they will want to get more electron to become B minus, B2 minus, and B3 minus. Look at, for example, in the data booklet, we have a real periodic table so big. So on the left hand side, for group 1 and group 2, okay, they have a one more electron, two more electron than the previous noble gas. So they want to lose one electron, becomes A plus, and becomes the electron configuration of fully filled one, okay, or A2 plus, or for 13, okay, become A3 plus, okay. On the contrary, for the non-metal, they want to get one more electron towards the right hand side, towards the noble gas, towards the completely filled octet. So for the fluorine, chlorine, bromine, they want to get one more electron and becomes fluoride, chloride, bromide, minus, minus, minus. Oxygen, sulfur, they want to get 2 minus. Nitrogen, phosphate, they want to get 3 minus. Okay. And this is the table, so no need to, it's such a rules, okay, you need to remember. For example, just make it easy. Metal become positive ion, we call it cation. Plus 2 plus 3 plus, okay, depends on the group, is 1, 2, or 13. And for the ionic compound, okay, non-metal wants to be a negative ion, want to be an anion by getting more electrons. So if they have one less electron, get one, two less electron, gets two, and that's it. Okay, so 15, 16, and 17 groups. Okay, look at them. One step close, two step, three steps. So mass, two mass, and three minus. And the transition metal, they have some special ability we talk about later. Property, they can have different charges. Okay. And then naming of the anion. Okay, remember the cation does not change the name. The positive ion still iron is still iron, copper is still copper, so anion does not change the name, but for the cation does not change the name, but the ion they will change the names, okay? For the negative ion, anion they will change the name. For example, they will change the name by themselves, it's IDE. So fluorine becomes fluoride, chlorine becomes chloride. So by naming them, you hear them, and then you know that whether it is an atom or ion. Chlorine is atom. Chloride is ion. So you get used to this quickly. Okay, IDE, negative ion, anion. And then for the anion with oxygen, they have a suffix of ATE. ATE. For example, CO3 2 minus is called a carbonate. So if there are two kinds of ion with different number of oxygen, one is ITE, one is ATE. For the ITE one is they have the same charge. For the ITE one is one less oxygen. Okay, so less oxygen one we call it ITE. More is ATE. So sulfate sulfate. So it is a good table. Okay, so the nitrogen, if it is by itself with 3 minus, is nitrate, sulfate, phosphate, and there with the oxygen. Okay, less the number of oxygen is ITE, nitrate, sulfate, and phosphate. More becomes a nitrate, sulfate, and phosphate. Later on, we will learn an oxidation number. If they are described by the oxidation number, the bracket Bowman number, then they don't need to have difference name. All are ATE. We'll learn about it later. And exception is a hydrate. Hydrates can be H minus, and hydrate can be also be the covalent bond in. We'll learn about covalent bond later. So hydrogen is an exception. And then there are some more enamel formula for common and for ammonium ion, hydroxide ion, and hydrogen carbonate. And then what's the ionic compound? Easier, the positive ion and the negative ion bond together. Right? Strong electrostatic attraction. The positive and negative attract each other, and they form a packed system, and we call it ionic bonding. And ionic compound are formed. The ionic bond is formed by the electrostatic attraction between positive and negative ion and ion and cation. Okay, so the ionic compound as a whole is neutral. This is very important. This is the rules how you can find out how many anion and how many cation are joined together. It's by this concept they are neutral in charge. So when you have X plus and Y minus, the combination is contrary. YA and XB joined together, make sure they have the same charges, plus and minus, cancel, neutral. Okay, so of course, sometimes we can omit it. Okay, for example, it's a 2%, 2 minus. Okay, they join together. We don't call A2, B2, just A1, B1, and the 1 can be omitted. Call it AB. So when you look at it, it's AB. I don't read it. It can be plus minus, 2 plus 2 minus, 3 plus 3 minus. Okay. So you don't solve it, okay? So for example, iron sulfate, okay, they join together becomes Fe2S3, okay? Of course, by this ionic formula, you can lower the charge of the ion too, especially when the ion can have easy charges. Metal it can different number of charges, okay? Binary ionic compounds are named with the cation first, low change of the name, followed by the anion. Anion has to change. Okay? For one Fe2S3, we call it iron, low change, iron sulfate, because this is S2 minus. Okay? And the 3D structure of the ionic compound, how the diagram behind is the 3D structure. It's very fancy when we will learn about it later, but actually, not a lot. In the university level, you learn a lot. Phase FCC, BCC, wow, very wonderful idea. Okay, we have some mathematical model for it. For now, to us, just join some simple one is okay. Very simple one is okay. So with the structure of ionic compounds, okay, ionic compounds has a high melting point and high boiling point. Okay, low volatility, brittle, and does not conduct electricity in solid state because they have a strong attractive force with each other. In solid state, they form a lattice. They can move with each other easily. So they become hard to break, high melting point, high boiling point, okay? And low volatility, they can't leave the solid easily, great attraction. And brittle, they can't deform because they have a rigid structure, okay? Too rigid. Sometimes not to be too rigid, a bit more flexible, right, guys? And does not conduct electricity because the iron, they have iron, they have charge, but they can't move, okay, in the solid state. So property of an ionic compound, ionic bond is strong, very important concept. All the things come out from here. So melting point, boiling point is high, volatility is low, okay, can't escape, okay. And in solid state, ionic compound form a three-dimensional giant structure like this, okay. We call it giant structure. We call this giant structure lattice, okay, of regularly repeating units, okay. And it resists a deformation, so it's brittle. If you really want to deform it, it will break. Sorry, it can't break. Okay? It's not flexible. For example, A plus and B minus form a cubic structure, okay, for a simple one, okay. Each A plus is surrounded by 6 B minus, and each B minus is surrounded by 6 A plus. We call it a cubic structure, okay. And then in solid state, as the ions are fixed in the lattice, okay, ionic bonds, so they can't move around, so conductivity is weak, okay. But in molten state, they can move. Right? In aqueous state, even they are dissolved in water. Okay, so the ions can move around to contact electricity, so the conductivity of molten and aqueous ionic compound is high. The most important we think about molten. For some other thing, okay, maybe in the molten state they don't contact electricity too. But for solid, molten and aqueous both contact electricity. And do you remember dissolve? Break the bond. Okay, although ionic bond is strong, okay, the polarity of water is also strong. So the polar bond of water is strong, so they can break the ionic bond. Okay, so basically all the ionic compound is soluble in water, but organic solvent, okay, is not non-polar in general. So molecular solvent cannot dissolve ionic compound. So this is the property of the ionic compound. So do you remember it? High melting point, high boiling point, right? Less volatile because they are fixed in the lattice, okay, three-dimensional lattice, okay. For the simplest AB, it is a cubic structure, okay. Each one is surrounded by 6 other ions. And also remember for the solid, okay, in the solid state, of the ionic compound, they cannot contact electricity because of fixed. But in molten state or aqueous state, they can. And the polarity of water is strong. It can break the ionic bond. So the water can dissolve ionic compound. So ionic compound basically generally is soluble in water, but not in organic solvent because organic solvent is non-polar. The bond between organic solvent is too weak. They can't break the ionic bond. Okay. So the lattice enthalpy is another concept. How much energy is required to break the bonding, break the solid ionic compound, separate them into gases. Okay. So down the group, okay, the ionic radius increases. Okay, so the ions separate more, so the attraction between them is weaker. So the lattice energy, the energy required to break the bond is lower, and the melting point is lower too. Okay, and lattice energy will give a definition next page. Okay, from the data book. The lattice energy, lattice enthalpy is the energy required. Okay, lattice enthalpy is a measure of the strength of the ionic bond in different compounds. The larger the lattice enthalpy, the larger the bonding. So down the group, the bonding is weaker, so the lattice enthalpy drops. Okay, you don't need to remember it much, but you need to interpret the data from the data booklet. Okay, for example, you look at the data booklet. You have a 16, section 16 is about lattice enthalpy as this 298.15 Kelvin. Remember what's that? Okay, this is the 25 degrees Celsius, the SATB situation. Okay, the lattice enthalpy is the energy required to break down the ionic compound in the solid state to gas state. But still the ion. Okay, still the ion. This is the definition, and then they have the data down there. Remember, the higher the lattice enthalpy, the higher the bonding, right? And you can see clearly, okay, this phenomenon down the globe, okay, far away. So the ion separate more, so the ionic bonding is weaker. So lattice enthalpy is also lower. On the right hand side also. So when they get bigger, the biggest one, okay. All are +1 and -1. You can see from the periodic table, the lowest one, okay. And also compare this one, okay, for the silver one, okay. Silver fluoride, silver chloride, bromide, iodide, okay. It is increasing down the groups, right? So the lattice enthalpy also decreases, but that decreases a little bit, not that drastic, okay. So you can do this comparison, okay, when they go down, okay. Magnesium, calcium also drops, okay. We can see magnesium oxide, calcium oxide also drops. Okay, so you can see the ionic compound, the lattice enthalpy drops down the groups, okay, because the ions are far away because the ion is bigger. Thank you for your going through this with me. Okay, you can see I'm not a fancy thing. You can go to the internet to search for the out of syllabus IBDP stuff. Okay, they have a lot of great structure. You can serve BCC, FCC structure of ion. You can see a lot of fancy drawing, great theory, but all of them are out of the IBDP scope, so I don't mention it here. Okay, I promise all the things we discuss here is absolutely IBDP required and essential. So follow us, okay, work together, learn it bit by bit, and then we can understand the whole IBDP's curriculum for chemistry clearly. So see you next week. If you like my sharing, remember, like, subscribe, and share it with your friends, okay? See you guys. Bye.